All right, chemistry, let's start our second video lecture for the combined sections in Chapter 8, Sections 2 and 3. We're going to start talking about single displacement reactions. Okay, so in a single displacement reaction, also known as a replacement reaction, one element replaces a similar element in a compound. Now, before we get too far into this, I want to point out that a displacement reaction is the same thing as a replacement reaction. You'll see that when something has been replaced, it has been displaced. When something has been displaced, it's been replaced. So please don't freak out and lose your mind if you hear me or someone else say a single replacement reaction or a single displacement reaction. They are the same thing. Now, many, and in fact for the purposes of this course, single displacement reactions take place in aqueous solutions. So keep that in mind. They take place in aqueous solutions. Single displacement reactions can be represented using the following general equations. Now we have A plus BX reacting to form AX plus B, or we can have Y plus BX reacting to form BY and X. And the key thing here is this word similar. Okay, in our first example here on the left, we have A and B are both metals. And so A is only going to replace B because a metal will only replace a metal. Similar will replace similar. Over here on the right, we have B as a metal, and we have Y and X as nonmetals. And so we see Y replaces X to bond with B, so it's nonmetal replacing nonmetal. Similar replacing similar. One of the things that we will finish up today with is something called activity series, the activity series. So don't freak out about this right now, but what I want to point out here is that aluminum in this reaction here, in this single displacement reaction, aluminum is going to displace lead. Aluminum is not going to displace nitrate because aluminum, okay, in the in solution, in the aqueous solution, is a +3 charge. Lead here is going to be a plus 4. No, it's gonna be a plus. So we have a metal cation and a metal cation. This is a negatively charged polyatomic ion. Negatively charged polyatomic ion. So the positive charge is going to replace a positive charge. The positive charge is not going to replace a negative charge. And so aluminum is going to replace lead. Now there is the possibility that this free element right here won't replace this at all and no reaction will occur. That's going to occur if said element is less active. But here, aluminum is more active than lead, so aluminum will replace lead to form aluminum nitrate. Now, this one is simpler than you might think as long as you can lock onto one idea. The displacement of hydrogen in water by a metal. Here, we're going to talk about two different situations in which a metal will displace hydrogen. And you might remember, I just said, like displaces like, or similar displaces similar. A metal will displace a metal, a nonmetal will displace a nonmetal. But here, we have a metal displacing hydrogen, which is a non-metal. So how does that work? Well, hydrogen is a bit of an exception because remember, in previous chapters, we have pointed out that hydrogen can act like a metal sometimes, and it can act like a nonmetal sometimes. Now, strictly speaking, it most truly is a nonmetal, but when it is paired with highly electronegative elements, it acts like a metal. It's not a metal, but it can act like a metal. So, if hydrogen is paired with something that's pretty electronegative, a metal will displace hydrogen. Now, the most active metals, such as those in group 1, okay, main group 1, they will react vigorously with water to produce a metal hydroxide and hydrogen. A metal hydroxide and oxygen. So here's our metal, here's our sodium, okay, main group 1, very active element. Put it with water, it's going to react with water to create a metal hydroxide. It's sodium hydroxide. Sodium is the metal, here's the hydroxide, so metal hydroxide, and hydrogen gas. It's H2 because hydrogen is a diatomic molecule. So here we have a metal reacting with water to create a metal hydroxide and hydrogen. Now, that's for the more active metals. If we go down the list to the less active metals, and again, you don't have access to this list yet. You will by the end of this lecture, but right now you don't have access to this. But for the metals that are less active, for example, iron will react with steam. Okay, it will not react with just regular old liquid water, for example, cold water. It has to be water that is so hot that it's entered the gaseous phase. It's water that is above 100 degrees Celsius or 212 degrees Fahrenheit. The reason that is because iron is, it will react, but not very much. It is a less active metal. It's not bringing a lot of activity to the table, so whatever it's going to react with has to bring the activity to the table. And so what is present in steam that's not present in liquid water is additional temperature, additional heat, additional kinetic energy, which is going to allow the reaction to progress. Without that additional heat, this reaction will not progress. And so if you put iron in cold water, you will not get this reaction. If you react iron with steam, right, with gaseous water, see this G right here, H2O-G, yes, this reaction will occur. But for these less active metals reacting with steam, we're not going to get a metal hydroxide like happens up here with our sodium. We're going to get a metal oxide and hydrogen gas. So notice how there's no hydroxides bonded to this solid iron compound here in the products. This is just an iron oxide and hydrogen gas. We can displace hydrogen, the hydrogen from an acid with a metal, because again, with an acid, the hydrogen is acting like the metal, right? It's balancing out the negative charge of the anion, and so a metal will displace the hydrogen from an acid. The more active metals will react with certain acidic solutions, such as hydrochloric acid or a dilute sulfuric acid, and they'll replace the hydrogen in that acid. The reaction products are a metal compound, which we call a salt, and hydrogen gas. So we have our metal, and we have an acid here. This metal is going to displace the hydrogen and bond with here the chlorine. So here we have the magnesium bonded with chlorine. Now notice that these subscripts are different here because when magnesium bonds with chlorine, you have to have 2 chlorines per 1 magnesium to balance the ionic charges. So you will have to do that in this section. I hope you don't freak out about it. Moving forward to halogens. Now we're going to talk about nonmetals. We've talked about metals a couple of times now, but we're going to talk about nonmetals as well. And we're going to use the same idea. Fluorine, okay, talking about the halogens, main group 7 or group 17. Fluorine is the most active halogen, meaning it's the most reactive halogen out of all the halogens. Fluorine can replace any element that is lifted below it, meaning the rest of the halogens. Fluorine can replace all of the halogens. So the general rule is, in group 17, each element can replace any element below it, but not any element above it. And this only works for the halogens, by the way, so don't try to do this with metals. And so we see, if we're looking at the periodic table, we see that chlorine is listed above bromine, and so this reaction will take place. Chlorine will replace bromine to yield a potassium chloride, and then free bromine. Fluorine, since it's at the very top of the halogens, it definitely will replace chlorine to yield a sodium fluoride and then free chlorine. But when we look at this potential reaction here, bromine is listed below chlorine on the periodic table. And so that means that bromine will not replace chlorine in this potassium chloride. And so that means that just no reaction will take place. If it's not going to replace this chlorine, then the bromine is going to do nothing. So we write no reaction. No reaction will occur. Let's move on to double displacement reactions. Remember, a double replacement reaction is the same thing, so don't get confused about that replacement-displacement issue. In double displacement reactions, the ions of 2 compounds now, exchange places in aqueous solution, still in aqueous solution, to form 2 new compounds. 2 compounds. 2 compounds on the reactant side, 2 compounds on the product side. That's your big red flag for a double displacement reaction. Now, one of the compounds that's going to be formed is usually a precipitate. an insoluble gas that bubbles out of solution, or a molecular compound, for example, water. Usually, not all the time, but usually you'll see one of those things in a double displacement reaction. The other compound is usually going to be soluble, and remains dissolved in solution. So let's look at the general equation for a double displacement reaction. A double displacement reaction is represented by the following equation, the AX and BY. Notice that those are two compounds. In both situations, they're bonded to something. Those are two different compounds. Here's a compound, here's a compound. That's the reactant side. Then we go to the product side. Here's a compound, and here's a compound. There's no free element. There's no element that isn't bonded to something. So that's your big red flag that this is a double displacement reaction. Now, the reason that precipitates form, and in the last section we described the formation of precipitate as a good indicator that a reaction has occurred. The reason that precipitate is forming is because the resulting attractive forces between those two ions are so strong that the water doesn't have the ability to dissolve it. The bond between, in this example that I have written down here, here's my precipitate. See, it's a solid. So it's coming out of solution because we have aqueous and then aqueous. A solid's coming out of solution. The bond between this lead ion and these iodide ions are so strong that water cannot break them apart to dissolve them into the aqueous phase. Similar things are going to happen here. We have the formation of a gas. H2S, it's a gaseous phase, meaning those two things aren't going to dissolve into water. They are going to hook together as gas and fly away. Again, because the attractive forces between those two ions are great enough that it doesn't happen. Same thing with the water there. Water is not going to be dissolved by water. It's just going to stay water. And so it's in liquid form. Again, note this G right here for the state of phase and this L right here for the state of phase. Moving on to our last type of reaction, combustion reactions. In a combustion reaction, a substance combines with oxygen. Okay, there has to be oxygen. If there's no oxygen, it's not a combustion reaction. So the presence of oxygen is required of all combustion reactions. In a combustion reaction, the substance combines with oxygen, releasing a large amount of energy in the form of light and heat. Now, we can combust almost anything, meaning we can combine with oxygen almost anything. We can combust hydrogen, in which case we combine the hydrogen with oxygen. When you combine hydrogen and oxygen, you get water, right? So burning this actually creates water. We can also combust a hydrocarbon, which is one of the archetypes that we'll need to be familiar with. This is a combustion of a hydrocarbon known as propane. So we have oxygen combining with this hydrocarbon. It's a hydrogen, carbon, hydrocarbon. When we have carbon present in the combustion reaction, the products will always be carbon dioxide and water. Now, the ratio at which they occur can change based on the hydrocarbon, based on what's being combusted, but it's always going to be carbon dioxide and water. So keep a lookout for that. If you're combusting a hydrocarbon, it's going to be carbon and water. If you're just combusting carbon, like pure carbon, pure C, there's no H here, then you're only going to produce carbon dioxide. If there's no carbon but only hydrogen, you combust that, you're going to generate H2O, water.
Methane, like many fossil fuels, can react with oxygen in a combustion reaction, releasing heat and forming carbon dioxide and water. The amount of oxygen available is very important for this reaction. When the supply of oxygen is limited, carbon monoxide, a poisonous gas, is formed. At very low oxygen levels, soot, or tiny pieces of carbon, are formed.
Now, this diagram that I have for you here is a very important one, very good one that I hope you use for studying quite a bit. It's a 5-pointed star, and 5 points, 5 different types of reactions: combustion, decomposition, synthesis, single displacement, and double displacement. Not only do we have the names of each type of reaction that we need to be aware of, we have examples of each. we have a description of each, and then we have a graphical representation of each. So this is a great diagram for you to use to study. Now I want to go through a very simple dichotomous key for identifying reactions and then predicting products. So ask yourself, looking at an equation and you don't know what type it is there only one reactant? If yes, then it's definitely a decomposition. So remember that. If there's only one reactant, it's definitely decomposition. Then ask yourselves, are the reactants either two elements or two simple compounds? If yes, you probably have some sort of synthesis reaction, right? Simple things coming together, synthesis. Ask yourself, are the reactants oxygen and a hydrocarbon? Then you're looking at a combustion reaction. Fourthly, ask yourself, are the reactants an element and a compound other than a hydrocarbon? If yes, you probably have a single displacement reaction. And lastly, are the reactants two compounds composed of ions? Then you probably have a double displacement reaction. Skip that. Those aren't supposed to be here. All right, objectives for section 3. This won't take that long. Just have a few slides. First off, I want you to be able to explain the significance of the activity series. Then secondly, use that activity series to predict whether a given reaction will occur and what its products will be. So the ability of an element to react is referred to as the element's activity. Again, interchangeable with the word reactivity. The more readily an element reacts with other substances, the greater its activity is. So an activity series is a list of elements organized according to the ease with which the elements undergo certain chemical reactions. Now for metals, right, that want to lose electrons, greater activity for a metal means greater ease of loss of electrons forming those positive ions. For a non-metal, greater activity means greater ease of gaining electrons to form negative ions. The order in which the elements are listed is usually determined by a single displacement reaction in aqueous solution. So remember that. It's usually determined by a single displacement reaction in aqueous solution. The most active element is always going to be placed at the top of this series. So everything listed at the top can replace anything that follows. Anything at the bottom does not replace anything above it. The activity series can be used to help predict whether certain chemical reactions occur, and that's what you are going to use it for. So here are my examples. I have an activity series for a halogen, I have an activity series for a metal, and yes, you will have access to this as you work on your assignments and as you work on your assessments.
An activity series is a categorization of elements based on their reactivity. For example, alkali and heavier alkaline earth metals react readily with cold water, oxygen, and acids. Lighter alkaline earth metals, aluminum, and some transition metals will not react with cold water but will still react readily with steam, oxygen, and acids. Some heavier metals will react with acids and oxygen but are unreactive to any sort of water. Other heavier metals will react with oxygen but are inert to acids and water. A few transition metals, such as gold and silver, are very unreactive.
Sorry, robot lady. Didn't mean to steal your thunder. All right, guys, that's going to do it for this section. I will see you next period.